In Chapter 14, we'll be handling the last of the Rosalind challenges that I chose for this book. And if we jump over to the Rosalind page, it has a nice description about why this is an important problem, trying to find the portion of DNA that can be transcribed into RNA and then translate that into protein. So that is the problem that we're trying to tackle in this. And it's going to bring together a lot of skills that we've used in previous chapters, and I think that makes the solution kind of come together rather quickly. And so it's going to include reading a FASTA file, which we've done before, taking the reverse complement of a sequence, using slices, finding k-mers, for loops, translating DNA, and finally using regular expressions. And so one of the things that we're going to have to do here too is also figure out how to, as we're going through the frame shift, how to cut off a string so that it's easily divisible, so it's evenly divisible by the codon size, which is going to be 3. So a little bit of math that we're going to do there. We're going to talk about string find a little more, and then a new function called string partition that we haven't used. And finally, we're going to get into how we can write a regular expression in a particular way using comments to help us understand and document the solution that we come up with. So to get started, I would encourage you to go to the top level of the GitHub repository and make sure you do source.vnv bin activate, and I always like to do that in 2 different windows. So I'm going to do that over here, and then I'm going to go into the 14 ORF directory. And the first thing I'm going to do is something I've shown here a couple times. There is in the bin directory here, there's something called all test, and the name of the program, what this is going to do is run through each one of the solutions and copy it to the program name that I give it, which is going to be orf.py. And I'm just going to verify that all my problems do work correctly. And while that's running, we're going to talk here a little bit about what we're going to be doing here. I'm going to copy the first one to orf.py, so that's already been done. I can see they all work, so I now have an orf.py that fully works. I'm going to look at the help document, the help output here, and you see here it accepts a single input FASTA file, so you should be able to do that very easily now with what you've already learned. And let's see, so we have this first input, which is going to have, it's going to be a FASTA file. And let's look at the contents of that. It has a single sequence in it, and so this sequence needs to be read, and then it needs to be turned into all of the possible ORFs, which are open reading frames, and those need to be translated into a protein sequence. And it does not matter the order in which these are printed. The test suite will simply make a set out of them, and so it won't matter what the order is. So that's what we're going to be doing. If you, as always, if you think you know how to do this, or even if you don't think you know how to do this, I encourage you to first go off and try writing your own solution to this, and then come back here. Or if you just want to follow along, I'm going to show you how I'm going to get started. So I'm going to start from scratch with a new py and open that ORF up, and it's going to be straightforward. I just want a file here, and I'm going to get rid of everything that's not file, and I'm just going to change that to a positional argument by getting rid of the leading dashes, and it's going to be called input FASTA file. And I will at some point after I've done all of these videos, I'll probably have a follow-up video showing you how to do this without using the argparse file type, which I know is deprecated. But because the book was written this way, I'm just going to go ahead and keep using it. And to get started, let's just start off by printing args.file.name. I think that's what I show here in the book. And I show you how you can create a get args here. And so yeah, let's get started here. I'm going to run orf with test inputs 1.fa, and it prints 1.fa. So that is a good way to get started. We now have a reasonably documented and Python program that accepts a single input file. It must be a readable text file because of the argparse file type, has good documentation, and we're able to access the slot called file, and then inside of that there's an attribute called name for the file name, and we can print that. So that is how we get started. So how do we write the actual meat of the program here? And so I have a suggestion that there's a number of steps, and it might be useful to write out something we call pseudocode, which is here I've actually written it indented to follow along with the way that I would indent and create these blocks and loops in Python to help me kind of see the structure of the program. So the first thing I need to do is iterate through each sequence, and those are going to be DNA sequences in the file. And I know how to do that using bioseq.io. And then I need to transcribe the sequence from DNA to mRNA, which we've done in a previous chapter. So I would recommend you go back and do that however you want. Then we're going to iterate through both the forward and the reverse complement of the mRNA. And then we're going to do something we haven't done before, which is go through each one of the 3 frame shifts. So starting at the 0th position, and then moving over by 1 base, and then moving over by 2 bases, so that we get all the different codons in this sequence. And then we're going to take that frame shifted subsequence, we're going to translate that into protein, which we've done before. And then finally, we're going to have to find the ORFs that are in that protein, which is going to be a sequence, an amino acid sequence that starts with an M and ends with a star. And so we've seen how to translate protein, and we've seen that, the seq, there's a method there that will translate the entire string and we'll go all the way through all the different stop codons, and we'll represent them with stars or asterisks. So you should probably be able to do all of this without my help. And so if this is a good way for you to get started, I would encourage you to do that. So I'm just going to keep going here. The first thing I'm going to do is I'm going to have to bring in, up at the top here, I'm going to bring in from bio import seq.io so that I can go down here, and instead of printing that, I'm going to print, let's see, what do I print? Oh, I'm printing the sequence to get started. And if you recall, the rec.seq is actually the seq object, and so I'm forcing it to, I'm coercing it into a string, and so that I can see that. So let's see, I'm going to run ORF, and I'm going to give it with test inputs 1.fa, and I should, here we go. I see now the contents of the file. I'm seeing the sequence printed there. So here I'm showing that I had to break it here for the book. And so the next thing I need to do is to change all the T's to U's. So that's what's going on here, translating that into mRNA. And then I'm showing here how to print the forward and then the reverse complement of that mRNA. And then I'm showing you, then the next step you should do is instead of printing those, print the protein sequence for the forward and the reverse. And once you get up to that point, now you have to get into something where you're shifting through the sequence. So I'm showing it here represented by just a number of some numbered positions here, but from position 0, we would start at 0, 1, 2, and then the next codon is 3, 4, 5, and then the next codon is 6, 7, 8, and then we don't need the 9th position. So when we take this string 0 through 9, we'd actually want to cut off 9 so that we only get a string that's evenly divisible by 3. And this is important because of BioPython here. If you choose to use the BioPython to translate the mRNA, it's going to give you this warning if the length of the sequence is not a multiple of 3. So that's what's going on here. So for the first one here, we would cut off the 9. Then when we shift over to the 1, we've cut off the 0, so we don't need to worry about it. We have a sequence that is evenly divisible by 3. And then when we shift over to the 2, we see 2, 3, 4, 5, 6, 7, and then 8 and 9 need to be cut off because that's not evenly divisible. So as we shift through this, we're going to end up getting shorter protein sequences, and that's completely fine. So I have this idea when you get to this point in your program that you should create a function called truncate. Given a sequence, some k that is the division, that is the modulus here that we're going to be using to figure out what we need to cut off. And so for our instance here, we'll be passing a k of 3. If you wanted, you could just hard code that so that you're only passing the sequence And you know, this, it's an idea. You know, you could write this function to, you know, to do this for 2 or 4. Really, in a biological setting, it's probably unlikely that you would ever use anything but 3. And so you're welcome to hard code that, and it will make writing this a little bit simpler. And so, and in fact, I only show tests that only use 3 here. But there'd be no reason, honestly, if you're passing k of the size here, you should probably pass a different size of k and verify that it works for that as well. So once you have this truncate function working, then you should integrate that into your code. I do recommend that you just use the bioseq function to turn the mRNA into protein, but you will need to truncate it. And so when you do that, you'll see that we have a longish protein sequence here, and then it gets a little shorter as we go through the frame shifts. So what we see here is that we get wildly different protein strings as we shift through. So these first 3 are for the forward sequence, and the last 3 are for the reverse complement sequence. And we see here we get entirely different protein strings depending upon the frame shift that we're in. So once we get to this point, the question is, how do we find the ORFs in the protein? So how are we going to go about finding these ORFs? And what I'm showing here in this example is that in this string, there are actually 2 overlapping open reading frames. One starting with this M and going all the way to the end, and then starting with the second M and going all the way to the end. And so we are going to need to find both of these strings for the way that the Rosalind grades the exercise. And so I recommend maybe thinking about creating a function that just finds ORFs. So given a string of amino acids here, we want to return a list of the strings of the ORFs that are contained in this string. And so there could be multiple, or there could be 0. And so to start off, it's nice that we could just define a function using these type hints, if you like. We have a nice doc string here to explain what this function does, and then we start off by just returning the minimum amount of information that we need to get this to compile and to work. And then let's think about how we would test this function. So now that we have this function, we can write this test where it's always good, I think, to start off by passing the empty string. When we pass the empty string, we expect the empty list. And this test will actually pass. The other ones will fail, so the test will fail, and that's fine. But we know that given a string that just has an M but no stop codon, that we should not find anything. If we have a string that only contains a stop codon, we should find nothing. But if we have a string, here's the minimal. So here I've encoded 3 things that essentially fail. But they fail in a way that I expect. So I would expect to find no ORFs given these bad inputs, but it doesn't mean that the function is going to throw an exception or in some way fail. It's doing what it's supposed to do. And so technically right now all 3 of these will pass because the function is just returning an empty list. But here the minimal string that will return an ORF is M followed by a star, an asterisk. And what we should actually return is just the M. We're not interested in the stop codon. So it's good when you're writing these tests to think about the minimum information that will get your function to pass, and then go up from there. So here, given this string that actually contains 2 overlapping, and this being the example here, given this string, I do expect to see these 2 different ORFs returned. And if I add another M after that, I still expect to only see those 2 strings because there's not another stop codon after that to produce a 3rd one. But if I did then throw in another stop codon, then I expect now to find 3. 2 in the first part, so this part still returns 2, and this last part now returns 1, and so I get back a total of 3. And this is a decent minimal little test. It would be enough to it's certainly enough to pass the Rosalind exercises. And if you are, if you're writing code and you go about trying to write code like this, and you find that, for all of your efforts to write a good tested function, that you find some input that it fails on, then you add that to your test, and you verify, you go add it to your test, you verify your function still fails, you fix your function, and then you now have that as a permanent test that will be part of the test suite going forward. So given, if you, I've kind of walked you through what you would need to, all the pieces that you need to pull together to write a solution. So again, I would encourage you, if you haven't yet, stop and go put these pieces together. I'm going to continue and talk about my solutions. So for the solutions, I'm actually going to take a step back here. I'm going to go back to the way that I was showing you how I might walk through this, and I think that part of what I try to bring in my teaching here is to get you to think about the process of writing code. That you don't just jump to an answer all the time. You need to take it step by step. So I recommended these steps, and so let's just go through these steps together. So we already have this. If we run this, the ORF program that I have, if I run it with test inputs 1, it's going to print this part. It's printing the sequence, and this is what we have here. We're printing the sequence. And so then I said, let's have it print the mRNA. And so, one way that I could do this is I could make this, I could say I think I just called it RNA, is equal to rec. Let's just do this. RNA is equal to the string of the record. And we're going to take that and we're going to replace T with U. And that's going to replace everything, and then let's just print RNA so that we have that. And then let's see how it works. I have an error here. Let's see, I don't have an extra parenthesis there that I didn't need. So now I'm able to print the RNA. I can say RNA or it's mRNA. The next thing I need to do is to use the reverse complement. And so I know that I can actually get I will call it rev C, and I can use the seek.reverse complement function that on RNA. And then let's print RNA, and then let's print rev C. I believe that should work just fine. And let's see, seek, I need to import seek. Here we go. Try that one more time. Okay, so now I am, looks like I'm getting the same, let's see. Nope, I'm using the wrong. So I got a little confused there. When I wrote the book, I was showing here the forward and then the reverse complement, and they both have U's. And when I was running this, I saw that when I used the reverse complement function here out of bioseek.io, it changed everything back to T's. And so I paused the video and I did a little researching, and I think that something has changed since I wrote the book a few years ago and the way it works now. But really, actually, it turns out we don't even need to do this. We don't need to replace the T with the U, because we're going to be using the seek translate function, which apparently is going to handle all that for us. So if I wanted to completely replicate what I'm seeing in the book, I would need to also replace T with U, but I just sat here and played with it, and I don't even need to do this step. So we can talk about that later when we get to it. So in order to just completely replicate what we're seeing in the book, this is how I could do this so far, and then we'll look at some shortcuts. So the next one is to translate these into the protein strings. So how would we go about doing that? Well, we could say for seek in RNA, and I can actually just do something like this. Well, I'll just leave that, and the rev C, so that we can go through each of them individually. Instead of printing the sequence, which we can make one change here, again with the process of coding. Let's just make the minimal amount of changes and then keep running our program. Okay, so that works. So instead, how can we print the translation of that? And I believe here, I'm just going to double check with my, sorry about that. Let's see, let me just double check with my solution, make sure. Yes, I'm going to be using seek translate. And so let's just kind of build up to that. And so instead of printing the seek, let's do seek translate. And then let's say toStop is going to be equal to false, because we don't want it to stop at the first. If we said toStop equals true, then it would stop at the first stop codon, and you see we don't get it, and then there's more coding stuff possibly after that one. So we don't want that to be true. And so now we're up to this point where we're printing these translated protein amino acid sequences. And now we want to, instead of printing that for the sequence, we want to step through with the frameshift. So we're going to, let's go ahead and trigger this so that we can see how to get around it. So instead of printing for seek and print that, let's say for, I'm just going to use I for the moment. Again, usually a terrible variable name, except in the case where it's actually going to be an integer value, especially in something like for I in range. And we're going to go up to 3, which is not going to be included. And what we want to do is we want to take sequence starting at I and going to the end. And let's see what we get when we run that. Now we're getting that this not a multiple of 3. So this is it's a warning. If we want, there are ways of getting Python to not print the warnings, but it would be better to just not generate the warning. And the problem is that it's this problem here. We're passing in a string that has bits on the end that it doesn't know what to do with, and it doesn't like that. It's untidy. So let's think about how we would do this. How would we bring in this idea of truncating? So I'm going to go over here and I'm going to insert this new function here, this idea, and just to step through what does it look like to write these kinds of things. And then we have this. Let me just go over here. It'd be a little easier for me to grab the test truncate. So let's just grab this little bit of code. We'll pop it in right here. And then think about let's run PyTest on ORF, and then we'll verify that our function is failing. So how do we go about writing this code? So what we want is we want to stop at the place where it's a multiple of 3. And so what we can do for that is that we can first look at the length of the sequence. So let's just drop into a REPL here, and let's say our sequence is A, C, G, G, T, and then let's just do that again. So we have something that's 8 characters long. And so if our K, we're going to set K is equal to 3 here, our codon length. Let's get the length of our sequence. It's going to be length of seek, and that is going to be 8. And so the end, what we want is going to be equal to the length, length minus the length mod by K. And that's going to tell us that we need to stop, that should be minus. So let's look at that again. And so 0 is not the right answer, but I realized this is a teaching moment. So let's go back. Let's go back to this statement where everything went wrong. What happened here is that Python parsed this. This is not incorrect syntax. And what happened is that length mod K got assigned to length, which then got assigned to end, and then that was 2. And then when I tried to run all this, length had been changed. Length was originally the length of the sequence. And so what I was trying to get was this. End is 6. That's where we actually want to stop. So just a quick teaching moment. This is actually correct syntax. It's syntactically acceptable. I'm not sure that it's really readable. I think it would be a mistake to write code this way. And so that's what was going on here. So what I really want to do is go from 0 to 6. So if we look at seek, going from 0 to 6, then we see that we have something that is 6 characters long, which is evenly divisible by 3. So if the sequence were equal to, let's change the sequence equal to now if we start from 1 character over, and now it looks like this, then the length of the sequence is now changed, and therefore the end is now changed. And so we want to go from the end is now 6 again. So if we take our seq starting from the beginning, because we've moved over, and we take it up to the end, then we see we also have something that's still divisible by 3. So let's prove to ourselves that this works. Let's run PyTest on ORF. Make sure that let's see, I guess I haven't saved it. Oops, I haven't actually brought in the code. Let's just take this bit of code here. Let's pop it into our function now. And so now when we run this, now we have something that appears to work. We have proven to ourselves here that with these 3 examples that it seems to work. So what we really want to do, let's build up to this, instead of translating seq at I, we want to truncate whatever seq at I is to something that's divisible by 3. And again, we could have hard-coded. Let's take a look at that. Let's run this with our test inputs 1. .fa. And so now we are able, let's go back to the book, and now we are producing this output if we look at it. This is how I was kind of stepping up to this when I was writing the program and trying to think about how am I going to get to the answer, just taking it one step at a time and really going back to that pseudocode that I introduced you to. If I wanted, I could have written this, without passing this. I could have hard-coded k is equal to 3 here, and then therefore I wouldn't be taking a k. Certainly an easier way to write this, and I would get rid of those, and then I would run PyTest on this, and I would see that this works just fine. And so another way, a simpler way, arguably, to write this, especially if it's always going to be 3. I will leave it the way it was because that's the way the book was written, but more food for thought. So now that we are up to this point, how do we find the ORFs in each of these protein sequences? And I suggested that we might start off with a little function called find ORFs. So let's just drop this in here, and it really doesn't matter the order of these functions. And I do like my little dividers. And so we have find ORFs, and then over here I have a test find ORFs. And of course we will be looking at multiple ways to find the ORFs, but in each case we will use the same test for this. So let's run for ORF, and list is not defined, so let's jump up here and add list to our imports from the typing module. And now we're going to run this, and we see our first 3 actually pass because we're expecting the empty list, and we're getting back the empty list, as we talked about in the introduction. So given a string, which is m and star, we're supposed to find an ORF that's just m. How would we go about doing that? Now we are finally to here the solutions part. So I would say one of the first things I could do, and I go over here how to write the truncate. So we've already done that. So I'm suggesting that we could use the index method, which we've looked at before. And one of the things that's dangerous about string index is that it will throw an exception if the thing it's looking for can't be found. So we're going to have this test that while we're finding M, the start codon, in the amino acid sequence, we're going to then use index to find the position of that. And then we're going to say if there's a stop codon after the start position, +1, so starting after the place where we find the M, if there's a stop codon, then we're going to get the stop codon out by calling index, and then we're going to simply slice in from the amino acid sequence from the start to the stop. Now that slice operation is going to actually produce a string, and it appears, and so then we're going to join this on an empty string to create another string, and we're going to append this to a list of ORFs that we're going to be returning from this. And then the amino acid sequence is going to be changed to, it's going to essentially be truncated to the position after where we found this start codon, the start amino acid, the M. And so this is a little bit kind of weird, a little dangerous, because we're actually mutating the input to our function. Not something I generally like to do, but I thought it would be worth talking about this as a method. And if it's the case that, that we find an M, but we do not find a stop codon, then we break out of this loop. And what you see is here, we're in a while loop that's going to keep continuing. But in the case that we find an M but no stop, then we just need to get out of this loop. And once we're done with this, we're going to return these ORFs. So what does that code look like? Well, I'm going to grab it from the solution 1 here, so I don't have to type all that out. And let's put this code in. And first off, let's verify, and I like to do the -v. So on the ORF, let's verify that our find ORFs is working. So this method does work, and so it's a question now of how we integrate this into our code. So instead of printing the translation of this, let's see. How did I go about doing this? I'd like to just follow along with what I did in the book. What I say here is, if it's possible that there's some translation, and I'm taking into account that possibly we're not able to translate this sequence. So if this returns something that is assigned to protein, and then the protein is found to be a non-empty string, then we're going to execute ORF on find ORF. So let me just grab that code. So this is what we had before, and now I'm just going to try to assign the translation of that truncated sequence to protein, and then find the ORFs in that protein and add them to the ORFs, and then finally I need to print them all. And so the container here for my ORFs, I believe I'm using a set. Yes, right there. I'm using a set. And that way they're just, if I find the same protein string, I don't want to print it more than once. So that's not really a problem with the Rosalind set. So I could have used a list. I think here would have been just fine. So does this work? We are running all of our tests using the inputs also from Rosalind, and that appears to be just fine. So we have built up our solution by using a lot of little pieces that we've kind of discovered before, and I'm just going to do double check. I'm almost positive. Let's just we'll discover this in real time with each other. I'm pretty sure I don't even need to do those translations. Right. So it turns out I think seek translate is going to handle the transcription from DNA to RNA, so we don't even need that part. So I could have even made this it's even simpler than what was in the book. So with that, that's our first solution. A second way to look about this is there's something called string partition, and it's a way of breaking a string on some character. And so let's go into the REPL here, and let's take this idea, copy and paste that. And what's interesting here is you see that we're trying to partition this string on the asterisk, and there are 2 asterisks. So it's going to break it up on the first one it finds. So it finds the asterisk, and then we get the first part of the string to the left of that, and then we get the part of the string to the right of that. Well, we get the thing that we're splitting on, the partition in the middle, and then we get the thing to the right of that. So we get 3 somethings back from that. And if we were to try to partition on a character that's not there, like say the character X, then what you see is we get the entire string in the left, and we get nothing in the middle or the right. So we're always getting back a tuple that has 3 elements. And so an easy way to determine that we're not able to partition that is simply look at the second argument. And if that's the empty string, then the thing that we tried to partition on wasn't found. So that's good information. That's what I'm showing here. So, for instance, we will come across this specific use case where we just have a string M and there's no stop codon, so there's nothing in the second position. So given that, if we have this string and we know that we partition it on the left side, we know that we should find 2 ORFs on this side, and then when we partition on the right side, we should find 1 ORF over here. And so here's a way to think about using partition. I partition the amino acid sequence on the stop codon into first, middle, and rest. So I'm unpacking that 3 tuple into the 3 elements over here. And if it's the case that there's nothing in the middle, then there's no stop codon. So I can break out of this loop. And you see here I'm in an infinite loop. So I'm just going to keep executing this loop of code until I hit the condition of breaking out. And then I'm going to establish my last position, and I have a second infinite loop in here where I'm going to find I'm going to look in the first part of this, and I'm going to say find an M starting at the position of the last place that I looked. It's going to initialize to 0. And if you remember that find does not create an exception. If it doesn't find anything, it returns -1. So in the case that it doesn't find a start position in the left side of what was just partitioned, then I'm going to break out of my loop. I'm going to be breaking out of this inner loop. And if that's not the case, then I have an ORF that starts in the first part that at this start position to the end of the string, because it was partitioned on the stop codon. So I can take from this place where M was found to the end of the string, and then I set my last equal to start +1. So I've essentially moved over to just after the place where I found the first M. And it's a bit complicated. I don't love this solution, but it was an opportunity to introduce to you string partition. So let's just grab this. It's really quite verbose. It's a long function. So we're going to be dropping this in here. And it should be no surprise that this works. The whole idea is that I'm showing that we're able to just change one part of the program. So we've got all of this. We understand this works well enough. But we're just trying to figure out the best way to find the ORFs. And we even have a test that can just help us hone in on the best way to find ORFs. So if you didn't know about partitioning a string on a character, that's pretty cool. I've also used it in the context of, say, a sorted list, and I've done this in Rust. So with a sorted list, I can partition the list on some condition. So it would essentially break the list into all the elements that are true for some predicate, and then finding the place in the list where that condition changes, and the things on the right side of that they fail that predicate. So partitioning, we think about partitioning in a few different ways in bioinformatics and in computer science, and it's just kind of a good function to know about. But for sure, the easiest solution here is going to be to use a regular expression. And so for that, I'm going to import RE, and with that, let's just go over here to the REPL and talk about a few ideas. So if I import RE, let's take this RE find all. We've talked about find all before, and so for instance, in this string, we want to find all the M's. Okay, that works just fine. What we want then, if we want to expand our regular expression to this is a character class that is negated. So if I had a character class that had character classes are started with the square brackets. Square brackets in case a character class. And so a star has a special meaning. It is a 0 or more of something. So if I want to use a literal star, I need to put it into a character class, or I need to / escape it. The way to negate a character class is to put the caret at the beginning, or this little hat. So if what I'm showing here is the pattern I'm looking for is M followed by anything that is not an asterisk, and 0 or more of those things. So here the asterisk now is its actual meta value. So it means 0 or more of the thing preceding it. So what it finds is it finds this string, MAMAPR, finds that, then it finds MP, and then it finds M. That's pretty good, but the problem is that we should be finding more. And so let's find another way to write this. So I need to add a stop codon, because first off, we don't want this last one because it's not followed by a stop codon. So it gets really kind of complicated to look at now, because we're literally looking for something that's also a meta character. And so when I run this, I'm seeing this invalid escape sequence, and it's because now we're backslash escaping this because we don't want it to be interpreted by the regular expression engine as some sort of qualifier, the 0 more qualifier. But now we have the problem where Python is trying to parse this string, and it's seeing the backslash in front of something, and it says, oh, like if that's a backslash T, I'm supposed to turn that into a tab character. And so what we want is a way to tell Python, don't try to interpolate this string, don't try to look at these escape sequence. So we're going to do that with an R. With a raw string. And so now when I use that, now I've got a regular expression that says M followed by 0 or more of anything that's not the star, and then it has to be terminated with a final star. And so now we see we have this string up to here, and then we have the MP star, but then we don't get the M because there's no stop codon after that. This is another way to write this would be to, instead of backslash escaping that, to put the literal star that we want to find in a character class. And now I don't actually need the raw string because there's no escape sequences there that Python is going to be worried about. So we are getting closer, but we know that there are actually 2 ORFs in this one, and we're only finding 1. And I always think that these are pretty to look at. A finite state machine diagram of the regular expression that we're looking for. An M followed by something that's not the star, and that can be repeated as many times as we want, and then something followed by a star. And we've already seen in chapters 8 and 11 that if we wrap this in a positive look-ahead assertion, then we will then find all of our ORFs. So let's just prove to ourselves that that is correct. We're now finding 3 instead of just 2. And so hopefully with that belabored explanation of all the complicated parts of this regular expression, you understand how to read this. And so if I want, I could replace all of this code here and find ORFs with simply find all of this pattern. And let's prove to ourselves that this works. Make testing, and it does work. It passes the unit test, it passes the integration test, and clearly that is the shortest way to write that. Now, it is a complicated regular expression, and it's very likely that within a day of writing this and closing the file, I will completely forget all the parts of that regular expression. And so if I come back to it, I will probably struggle with relearning it. And so I want to show you an oddity about Python, and I've mentioned this before, the fact that the adjacent string literals will be joined together into a single string in a certain context. So if I put this pattern in these parentheses, that's enough of a context now where this string will be married to this string, will be joined to this string, and on down into one string. So pattern here would then, all these bits, these parts would be concatenated into a single string. And what that allows me to do is to come here and put a comment on each line. The comments will be ignored, and these will be joined together into a single string. And so I can say here, this is the start of a positive look ahead to handle the overlapping ORFs. This is the start of a capture group. I want a literal M, and then I want it to be followed by 0 or more of anything that's not an asterisk. So this is the character class that negates the asterisk, and then the asterisk here is the meta character that says 0 or more of the thing that's just in front of me. This ends the capture group that is started here, and then I want to be, it must be followed by a literal asterisk, and then this ends the look ahead group, and then this ends the start of this. And now I can say return find all pattern in the amino acid sequence. And let me show you what that looks like in the code that I wrote. So there's just one thing I don't like about using this, and I have to change this to pattern. One thing about this is now if I were to, for instance, run this through my say I'm using black here to format my code, you see here it messes up all my nice, the way I lined up those comments. So if I don't do that now, it's just something that's a little bit annoying. So I can't run it through black or YAPF, yet another Python formatter. It will mess that up. So anyway, that you could put these on top of the lines if you want. That would be another way to go about doing this. So with that, let's just prove to ourselves it works. So 3 different ways to write that function for finding ORFs. Almost everything else we were just kind of pulling off the shelf. With especially bio, with the parsing of the FASTA file, with the reverse complement, the translation for us, we had to write this truncate to make the translate function happy, and we wrote our own little method here for finding the ORFs in the translated sequence, in the protein sequence. So going further, expand this out to handle multiple input files and write all the unique ORFs to some sort of output file. You should definitely be able to handle that at this point. You're going to need to add another looping here. You might actually move all of this into a single function that given maybe given a sequence, it's going to put all of this together and return a list of ORFs for a given sequence. And so you would have for each input file, for each record, and parsing that file as a FASTA file, adding the ORFs to some sort of a structure or printing them out, however you want to do that. So reviewing, we use the translate function, and in order to use that nicely, we wrote our own truncate function. We explored string find and string index and string partition, different ways of breaking strings apart. But in the end, I think the regular expression is again the way that I would go. Probably if I benchmark these on some big input files, I would likely find that that's the slowest way to go about it. And if it was truly a problem, I would write faster code, or maybe I would implement it in a different language, such as Rust. And the last thing is that regular expressions can be quite complicated to